Okay, we are off to the next chapter. Last time, before the holiday there, we finished up talking about really kind of chapter 4, 3. We did our bonding, and obviously we did our nomenclature. So now we're going to talk about, in this chapter, atomic mass. We're talking about grams, moles, Avogadro's number. We will talk about different types of formulas, empirical formulas, molecular formulas, and how to calculate those. So let us get started here. So first thing we're going to talk about is really the atomic mass, and a reminder that as we talked about when we did atomic number and mass number and all that good stuff, the atomic mass actually is the number that we see below the symbol there on the periodic table. And it is one of the fundamental properties of an atom. It's obviously related to how many protons, electrons, and neutrons that it has in it. But obviously, atoms are extremely small. You can't just like pick one up and like pop them onto a scale or something like that to weigh them. So typically in chemistry and in most sciences, whenever you can't maybe directly measure something, we oftentimes will choose something to use as a standard to compare everybody to. And for the case of atomic mass, they used a carbon isotope as the standard to sort of figure out the atomic masses that we see on the periodic table. And it was actually the carbon 12 isotope is what they used as sort of the standard. Carbon 12 isotope has 6 protons, also has 6 neutrons, and it has a mass of exactly 12.0 AMU. And AMU is a unit of atomic mass. It stands for atomic mass units. Not too many people these days use the Dalton. It is also sometimes referred to as a Dalton, but atomic mass unit is also a unit that, as we'll see as we go through this chapter, we don't really use all that much anymore here in chemistry as well, but it is the unit of atomic mass that we can take from the periodic table. So one atomic mass unit is exactly 1/12 the mass of a carbon 12 isotope. And when we do pull, for example, the numbers off the periodic table, like our hydrogen, if we look, it's like 1.008. Typically speaking, we do go usually to 4 significant figures, and really we can use it as a conversion factor. Basically, what that says is there's 1.008 AMU in an atom of hydrogen. And again, you could kind of use it, like I said, as a conversion factor if you want to figure out the mass in AMU. You can kind of use it like that, or you can flip it around and do a little dimensional analysis and use it as a conversion factor sort of in the other direction. So that is one way that we sort of can use the number that we see for atomic mass off the periodic table. As we'll talk about in this chapter, and as you may be familiar with, we oftentimes will use a more sort of useful number for us, which is molar mass, which gives us how many grams per mole there is of something, as we grams is a very common unit of mass that we use a lot. So that's a more sort of convenient unit that we use when we take it off. But again, this is value that you can get from the periodic table. Now, atomic mass, or sometimes referred to as the atomic weight, is the again the mass of these elements that we find on the periodic table. So how do they sort of figure out, what is the mass of all the other elements if we use sort of carbon 12 as a standard? Well, they do sort of a calculation. And for example, experiments have shown that the hydrogen atom is only about 8.4% as massive as the carbon 12 atom. So they basically could do a little calculation. For example, here, that is 8.4% converted into a decimal, divide by 100 or move the decimal place 2 places to the left times the mass of their carbon 12 gives us again about the number that we see for hydrogen there on the periodic table. Similar calculations have been done for pretty much all the elements that we see up there, and we can find that the atomic mass listed on the periodic table, again, underneath the symbol, and one version of atomic mass, again, is AMU per atom, or sort of the units that you can get when you pull that number off the periodic table. Now, if we use carbon-12, for example, as the standard, and it has a mass of 12 AMU, when we do look at carbon, though, on the periodic table, we actually do not actually see a mass of 12.00. We usually will see something like 12.01. And that is because what we are really seeing up on the periodic table is the average atomic masses. They are the average atomic masses of all the naturally occurring isotopes for that particular element. Remember that an isotope is the same element, but it has a different mass because it has a different number of neutrons. So it has a different mass number. So that is why when we look at something like carbon, we don't see 12, which is what we might expect since we're using the carbon-12 isotope as a standard. So something like carbon has carbon-12 isotope, also has carbon-13 isotope, and they do have different masses. One's about 12, one's about 13. And what we see is sort of the average value of all those naturally occurring isotopes. There's actually a calculation that you could do to calculate the atomic mass of an element based on the isotopes that are given. So you could calculate the atomic mass in AMU, and it basically is by taking the percentage of the first isotope times the atomic mass of the first isotope. And then what you do is actually add it. And this is something sometimes people screw up on. They want to multiply and everything here, but you actually add it. And then it would be the percentage of the second isotope times the atomic mass of the second isotope. And you really will just compete this sort of pattern depending on how many isotopes there are. Now, when we talk about the percentage, that is sometimes referred to as the relative abundance of a particular isotope. That's kind of the percentage at which it sort of naturally occurs. When we do it in the calculation, though, you do need to make sure you turn your percentage into a decimal point. So again, you could either divide by 100, move the decimal point 2 places to the left, but you should obviously do it as a decimal in this calculation. Now, obviously, 100% is like I have all the naturally occurring isotopes. So one of the things you typically want to do when you're sort of calculating these things is you want to calculate and add up all the percent relative abundance and make sure that it does equal about 100%. It may be a little above 100%, maybe just a little bit below 100%, but it should definitely be in the 100% sort of range. If you find yourself well short of 100%, then you're probably missing some type of isotope, or there's another isotope out there to get you to 100%. Questions on that there? So as I mentioned before, for example, if we take something like carbon, there's two sort of naturally occurring isotopes, carbon-12 and carbon-13. The carbon-12 occurs about 99% of the time, and the carbon-13 occurs about 1% of the time. Again, this is what I talk about sort of with our percentages. We look at our percentages and sort of add them up. It does equal about 100%. And we can then use that formula here. So this is our 98.89% converted into a decimal. So the percent of the first isotope times the atomic mass of that first isotope, which is 12. We then are going to add it to the percentage of the second isotope. That is basically 1.11% converted into a decimal. And that is the percentage of our second isotope in this case. And when we do that, we get that 12.01 value that we do see when we look again on the bottom of the periodic table there for carbon. Most people don't necessarily call it an average atomic mass. Most people just refer to it as an atomic mass, but it really is a sort of average value of all those naturally occurring isotopes. That also means that if you were able to sort of just pick out individual sort of carbon atoms or isotopes, you would never really find one that has a mass of 12.01. you would actually find one that is either like the carbon 12 mass of 12 or the carbon 13 mass of 13 and some change. But again, here we use these sort of average values to allow us to do calculations. And again, they are of those naturally occurring isotopes. Atoms are very, very sort of tiny, and to avoid these sort of small numbers, we sometimes will use something like atomic mass unit. If you want the relationship in terms of what that is in terms of grams, one atomic mass unit is 1.66 times 10 to the minus 24 grams, super small number. So again, this AMU also gives us an opportunity to use a little bit of a larger number, rather than obviously having to do calculations with really, really small sort of values. The average atomic mass of these guys, again, are weighted against those isotopes, and that's what we just talked about. You'll never really find one that's 12.01. So as I mentioned before, we can use this as a conversion, and we probably don't do too much of this these days, but we still can. So again, if we went to our carbon, we would see 12.01. That would really give us our two conversion factors of 12.01 AMU per atom. R an atom is 12.01 AMU. So if we have 431 atoms, we would use the conversion factor in the opposite location so that atoms cancel, and it would give us something like 5,176 AMU is the mass of about 431 atoms of carbon in this case. And again, we could do that for any element that we find on the periodic table. If we look over here at aluminum, again, you'll see 2698, which once again gives us our two conversion factors here. And here we're starting with 75 aluminum atoms. So once again here, we will use that so that the atoms cancel. We're going to multiply what's on top, and that'll get us 2024 AMU in terms of the mass of those guys. As I mentioned before, probably don't use AMU all that much as sort of a unit. We do use molar mass, which is grams per mole, as I mentioned, which, as we'll talk about, is numerically the same as the atomic mass in AMU, but it does give us in the end sort of a more usable unit in a lot of times of stuff that we do, which is in terms of grams. Question on that there. All right, so how do we know sort of, the relative abundance and the sort of percentage of each of these naturally occurring isotopes? We can use something known as mass spec, and the masses and abundance of isotopes are measured with a mass spectrometer. Atoms are basically ionized, they're sort of accelerated down a tube, and they're basically separated out and broken up by size and mass. And this helps determine sort of the naturally occurring isotopes. They do pass through sort of a magnetic field, also a little electronic field, and they get separated out on sort of the graph, and they come out based on their sort of masses. So this is the way we can kind of figure out the different percentages. So for example, if we look at sort of a graph here of, say, chlorine, we got chlorine 35, which is about that percentage. We got about chlorine 37, which is that percentage. So we can see here, based on how it's going to come out on the graph, chlorine 35 occurs about 75% of the time. Chlorine 37 is about 25% of the time. And as they will also break out in terms of their mass, will be a little bit different based on how they come out of the graph and where they end up. So we can find out the relative abundance, and we can also find out the mass of those isotopes by putting it through a mass spec, which looks something like this. Again, you throw your sample in here, sort of really heat it up. As it comes through here, it goes through an electrical field, and will also go through a magnetic field. And again, they will separate out on the graph through the detector. Lightest will sort of end up to the left there. Heaviest particles won't be bent as much and will kind of come to the right there. And it can kind of separate them out based on size and something like that. Yeah. Yeah, so it does break it up into the different isotopes because they have different masses, right? So as they go through those, the lighter things going to move a little quicker, right? Kind of heavier things are going to move a little slower. So that's going to allow them to separate out. And they will give sort of peaks based on sort of the percentage of how much is there. And they sort of measure those peaks and come up with like percentage, based on the overall that was in the sample. Other questions? All right, so why don't you try one here? Copper is 69.17%, copper 63 with a mass of 62.9396 AMU, and the rest of it is copper 65 with a mass of 64.9278 AMU. What is the atomic mass of copper in AMU? So those are the two isotopes. So give it a go, see what you come up with. Okay, so let's take a look. So in this case, we got a couple isotopes of copper. We got copper 63, and it occurs about 69.17% of the time, and it has a mass of 62.9396 AMU. We also have a second isotope here, copper 65. It doesn't tell us the percentage at which it occurs, but it does give us the mass of 64.9278 AMU. So in this particular problem, these are the only, obviously, isotopes of copper that's present, which means we can find our missing percentage by assuming 100%, right? Because them together would equal 100% of what we have. So to find sort of our missing percentage, we take 100% minus 69.17%. And that will give us really our percentage of copper that's missing, which looks like it's 3083. Now we know this guy is 3083%. And again, now we have basically everything that we need to calculate it using our formula that we talked about. So we'll do our atomic mass here is going to equal our first isotope, which will go with this one. Remember that we do need to convert our percentage into a decimal. So again, you can move the decimal place 2 places to the left, or you can divide by 100, whichever way you want to do that. We will times it by our atomic mass there of our first isotope. We will then again add it at this point, not multiply. We've got to do the same thing and convert our percentage here into a decimal. So again, if you don't want to move the decimal and just want to divide by 100, that will do it for you. And that will basically move your decimal point over. And we will end up with 0.6917 times 62.9396 plus 0.3083 times 64.9278. That's going to get you 63.55 AMU. Whoops, AMU. As our atomic mass here for copper. And again, if you look at copper on the periodic table, that is pretty much what you see there, 63.55 as its molar our atomic mass for copper. Any question on that calculation? Yeah. Yeah, so I would say just in general, anytime you're maybe calculating atomic mass or molar mass that we'll talk about later as well, usually 4 significant figures is usually where you would want to end up in terms of your answer. In this case, you would then still sort of go by most of the rules here, but that's usually where you want to end up, 4 significant figures. Yeah. Other questions? Okay. All right, so that is again how you calculate the atomic mass and how we get those values that we see on the periodic table. Now that we talked about atomic mass, we're going to really talk about a more useful version of it. But first, we're going to talk about our friend atomic Avogadro's number. I'll spit that out. And the idea of a mole. And in life, we have a lot of words that represent a certain amount of something. So when somebody says a dozen, we know that usually that refers to 12. Somebody says a pair, That usually refers to 2. Gross is usually like 144. So in chemistry, we do have a word that sort of represents a certain amount of something, and that is the mole. And the mole is abbreviated as MOL. And it's really important to remember that when you do see, for example, MOL in a problem or wherever you may come across, it is referring to moles and is not referring to molecules. That's a very common thing that sometimes people screw up on. They see MOL and their minds just sort of goes to molecules, but that is the abbreviation for mole. Had to get rid of something, so got rid of an E on that. And the mole is really the amount of elementary substances there are in 12 grams of the carbon-12 isotope. And 1 mole of anything will equal 6.022 times 10 to the 23. That is Avogadro's number. Now, it is the unit part of this that does change. So 1 mole of anything will equal 6.022 times 10 to the 23. These could be atoms. If you're talking about atoms, they could be molecules. If you're talking about molecules, could be particles. Could be pizzas, or shoes, whatever it may be. I would say probably in most cases, it's going to be atoms or molecules are the most common sort of unit that is used with Avogadro's number. And basically here, we use Avogadro's number as really a conversion factor, and it is the conversion factor that allows us to go from moles to atoms, or molecules, are backwards from atoms or molecules back to moles. So that is what Avogadro's number should be used for. It can be used as 1 mole over Avogadro's number, 6.022 times 10 to the 23 atoms. Or you can flip it around and use Avogadro's number up on top over 1 mole. So these are really the two sort of conversion factors that we use with Avogadro's number. Now, it's really important as well that you, frankly, do not use Avogadro's number everywhere. And that's also a very common issue that people have is like, I learned this number, I should probably just use it in every calculation I ever do. And you should not do that. So you really should only use Avogadro's number if you are given a number that's in atoms, molecules, particles, or you're asked to solve for something that's in atoms, molecules, or particles. Other than that, you should leave Avogadro's number on the side. So you shouldn't use it. Um, just to use it. Sometimes people use it like up front in the calculation, and then they end up dividing up front and multiplying on the back end and canceling it out. So we could apply Avogadro's number, by the way, to basically anything on the periodic table. So 1 mole of hydrogen would equal 6.022 times 10 to the 23 atoms of hydrogen. You could also apply this to things that are not just elements, but say things that are molecules like water. 1 mole of water would equal 6.022 times 10 to the 23. Here, the units would be molecules because water is a molecule of water. So you could apply Avogadro's number to just elements off the periodic table. You can apply them to molecules, compounds off the periodic table. Again, it still gives you the same sort of conversion factors. 1 mole of hydrogen, 6.022 times 10 to the 23 atoms, are 6.022 times 10 to the 23 atoms is 1 mole of hydrogen. And you can do the same thing with water. And again, basically going to use Avogadro's number as a conversion factor. Now, in addition to Avogadro's number, probably more used than Avogadro's number and really a sort of atomic mass is the idea of molar mass. And molar mass, as I mentioned before, is really a more sort of usable unit that we use. And we also get it in the exact same location off the periodic table is right there. That is also the molar mass, in addition to being the atomic mass. But when we use it for molar mass, there are different units, and molar mass has the units of grams per mole. And basically, whatever that number is, 12.01 grams of carbon in 1 mole of carbon. And basically, you say the molar mass of carbon is 12.01 grams per mole. We also could use molar mass as a conversion factor. And again, you could use it as 12.01 grams per mole. And by the way, when you do molar mass, the number always stays with the grams and it's always 1 mole. So the mole never has numbers. It's always 1 mole when you're doing molar mass, or the mole over 12.01 grams are the two ways we use that. Just like everything else there, we can also use molar mass for things that are molecules and things of that nature. So we had something like water. We basically just add up all the parts. We would go and find hydrogen on the periodic table. Once again, we would go to 4 significant figures when we're pulling those numbers off of the periodic table. And basically, if we wanted the molar mass here of water, we would go 2 times 1.008 grams per mole, which is for our hydrogens, basically. We would add it to 16 grams per mole, which is our oxygens, and that'll give us 18.02 grams per mole, which would be the molar mass of water. Once again, we could also use that as really a conversion factor, 18.02 grams per mole of water, or a mole of water is 18.02 grams. We're not going to use all those conversion factors. Obviously, we're just going to use whichever one we need, which is opposite of each other, but we can calculate the molar mass here. As you can see here on this page, numerically equal to each other. So what I mean by that is the AMU per atom is numerically equal to the grams per mole value that you get on the periodic table, which is why we could use the value there for either way. Most of the time, again, we use molar mass because grams, again, is that unit that is a lot more useful for us. So how does sort of all these things tie together? As you can see there, Avogadro's number, molar mass, all those things, they really do just tie together like we see in the middle. If you had 1 mole of carbon, it is 6.022 times 10 to the 23 atoms of carbon, and that would be equal to 12.01 grams of carbon. So that is how they all relate to each other. Same thing if you had 1 mole of water, that would equal 6.022 times 10 to the 23 molecules of water. And that would equal our 18.02 grams of water, basically. So that is basically how they sort of all tie together. 1 mole of a substance is basically equal to that many grams, and still equal to Avogadro's numbers worth of atoms or molecules. Any question on any of that there? Here's a 1 mole, some different substances, and if we took, a beaker, for example, a bunch of beakers, and fill them all up with 1 mole of a substance, of each different substances, they may appear to be looking like there's different amounts of it. And that is because 1 mole, for example, of sulfur is 32.07 grams, right? While 1 mole of carbon is only 12.01 grams, right? So although they do represent the same number of moles of each of those elements, each mole of an element represents a different amount of grams of that element. So they may appear to be obviously different amounts that are in there. All right, there's our conversions here. And again, as we saw earlier, our relationship between these things. So once again, if you got to go from grams to moles or backwards, that's going to be your molar mass. That's going to be your conversion factor to do so. If you need to go moles to atoms or molecules or back, that's going to be your Avogadro's number. So again, make sure you use it appropriately when you do that. Any questions on that there? I want to try one here. Calculate the number of grams of iron in 15.7 moles of iron. If we look up iron on the periodic table there, looks like a 5585. All right, so take a moment, set it up, see what you get. Okay, so let's take a look. So once again here, we want to calculate the number of grams in 15.7 moles of iron. Do I need Avogadro's number here? I do not, right? Again, there's no mention of atoms, molecules, or anything like that, so we don't want to use Avogadro's number here. We're basically going from, in this case, moles to grams, and that conversion is the molar mass that we get from the periodic table. That basically means that the molar mass is 55.85 grams per mole of iron. We also, again, could use it in the opposite sort of location there, or way, as a conversion factor to do a little dimensional analysis. So here we will start with 15.7 moles of iron. We want to go opposite to cancel, so we do want to use the molar mass in this form here. That's going to leave us with grams, and our moles here of iron will cancel. We're going to multiply our 15.7 times our 55.85, and that's going to yield us something like 877 grams of iron in this particular case. Sig fig wise, probably would look at the original number there, which has 3, and sort of round it off there to 3 significant figures. Any questions on that there? Oh. Again, this is the way you should show the calculation, dimensional analysis, conversion factor type of situation here. All right, so I want to try lithium here. We'll do lithium. Got this one here. We're looking for moles, and we got grams. So once again, that's a grams to mole conversion. That's going to be our molar mass from the periodic table. No mention again of atoms, molecules, particles, so no need to use Avogadro's number. That's going to give us off the periodic table there 6.941 grams per mole of lithium. Or again, we could use it in the opposite location if necessary here, 6.941 grams on the bottom. Here we are starting with grams, so we do want to get rid of that, which does mean we do need to use it here on the right-hand side so that we're really dividing by our grams so that they cancel each other out. Moles of lithium up on top. Again, the grams will cancel. That's going to leave us moles. So we got 77.8 divided by 6.941. That's an 11.2 moles of lithium in this case. Any question on that calculation there? Yeah.
Are you using the particular like formula or
Just setting up dimensional analysis, right? So just like we did with conversions, we're multiplying on the top, right? Dividing by what's on the bottom. And again here, all you have to think about is opposites cancel, right? So you get the units in the right location. Yeah.
so just make sure that
Yeah, so you want to cancel out obviously the units you don't want and end up with the units that you do want. In this case, we're looking for moles, so that's why moles has to be on top, right? Yeah. Other questions? All right. So let's try another one here. How many atoms are in 0.551 grams of potassium? Potassium there on the periodic table, little 3910. Okay, so let's take a look here. We're looking for how many atoms. So right there, that is the keyword that you do need to use Avogadro's number here somewhere along the way. There are in 0.55 grams of potassium. So we're obviously starting with grams. We want to end up at atoms. Really, the thing in the middle that ties both of those together are moles. And remember that to go from grams to moles, that's going to be the molar mass from the periodic table to do that. And to go from moles to atoms, that's going to be our Avogadro's number. That's going to allow us to kind of do the last conversion part. So we need a couple of conversions that we could maybe choose from. Obviously, our molar mass here, 39.1 grams per mole, or again, we could use it in the opposite way. We also know that in this case, 1 mole of potassium will equal 6.022 times 10 to the 23 atoms of potassium. That will give us really two conversion factors that we could use. 1 mole of potassium over 6.022 times 10 to the 23 atoms, are the opposite way, 6.022 times 10 to the 23 atoms over a mole. So starting with the number that was given to us, 0.551 grams of potassium, we're going to do this part first, which is our molar mass, which is over here to the left. Again, we want to go opposite so that our grams cancel. So we do want to use a conversion factor just like so. Moles of potassium is 39.10 grams. Grams here. At this point, if I stop my calculation, I'm in units of moles. I could get an answer, but in this case, I'm just going to continue the calculation. This again is why it's important, as we talked about previously, to set it up with dimensional analysis, because now I could clearly see that my moles are up on top, which means when I go to do the last part of calculation, I do need to use the conversion factor here on the right so that the moles cancel. And that means that Avogadro's number actually would need to go up here on top in this case for this to properly cancel. We are again going to multiply whatever here is on top. We're going to come back and divide by the bottom here. And in this case, we also want to make sure that we do use our exponent button when we punch in Avogadro's number. So we're going to take 0.551 times 6.022, exponent button 23, and hit equals, divide by 39.10 and hit equals. And that is going to get us here 8.49 times 10 to the 21 atoms of potassium. So it's a lot of atoms of potassium, but that is how much would be in 0.551 grams of it. Obviously, you could, if you wanted to, like I said before, get an answer after the first part of the calculation. I would not round too much and then continue on with the calculation. Any questions on that one there? Try a few more, just make sure. All right, I want to try both of these. How many moles of helium are in 5.46 grams of helium? And how many grams of zinc are there in 0.256 moles of zinc? Helium 4.003 and zinc. Yeah, let's take a look. So first one, we want moles and we have grams. So once again, this is going to be a grams to moles conversion. That's going to be the molar mass from the periodic table. That's going to tell us the molar mass is 4.003 grams per mole. Again, we can flip it around if we want to use it more as a conversion factor. So here we're going to start with our 5.46 grams of helium. We want to go opposites to cancel, so we will use it in the opposite sort of location as a conversion factor. Our grams here are going to cancel, and we will end up with 5.46 divided by 4.003. It's going to give us a 1.36 moles of helium. Once again, no mention of molecules or particles, so we don't need to use Avogadro's number. Any questions on that one there? And same thing here with the zinc. Remember that this is moles and not molecules, so that is moles going to grams, which once again is also our molar mass from our periodic table. And from the periodic table there, 6538 grams per mole is the molar mass of zinc. If we want to use it more as a conversion factor, we could also, again, flip it around if necessary. So starting with 0.256 moles of zinc. In this case, we want moles on the bottom, so we'll use it like the molar mass with grams up on top. That way the moles cancel, multiplying our 0.256 times 6538 gonna get us a 16.7 grams of zinc in this case. Any question on those two calculations there? All right, we'll let up there for today.